Bivariate data is data that concerns two different factors or variables together. A variable is an element or feature that is likely subject to change as time passes. Most bivariate data is represented on a scatter plot. Scatter plots display an explanatory variable plotted on the x-axis and a response variable plotted on the y-axis. This display of data can reveal an association between the two variables, direction of their relationship that is either positive or negative, form of the data, and the linearity of the relationship. An outlier is an extreme value located at either an extreme high or extreme low that shifts the association or scatter plot drastically. On this scatter plot seen here, number of years since 1900 is plotted on the x-axis, and the percent of the U.S. population that would vote for a female president is plotted on the y-axis. In this situation, the number of years since 1900 is the explanatory variable, and the percent of U.S. citizens that would vote for a female president is the response variable. It is seen here that there is a relatively positive linear association between the two variables with an outlier at the high extreme end of the data that could drastically alter the plot's association. Here are the keystrokes of how to create a scatter plot on a TI calculator. Correlation is the strength of the linear association between two quantitative variables. The infamous correlation coefficient is a numerical value ranging from -1 to 1 that describes the strength of the variables on a scatter plot. Values ranging closer to -1 or 1 are stronger, whereas values closer to 0 are weaker. There are a few conditions that must be met for correlation. The quantitative variable condition. This states that variables measured must be quantitative and not categorical. The straight enough condition. The association represented by the scatterplot must be linear or quote-unquote straight enough. The outlier condition. If an outlier is present, correlation should be reported both with and without the outlier included to show any drastic changes the outlier has on the association. Be sure not to get correlation confused with association. Association is a vague term describing the relationship between two variables, whereas correlation is a precise term describing strength and direction of the linear relationship between two quantitative variables. Also be on the lookout for any potential lurking variables. That is a variable that stands behind a relationship and determines it by simultaneously affecting the other two variables.
Chapter 8, Bivariate Linear Regression. The linear model is the equation of a straight line through the data that can summarize the general pattern with only a few parameters. Residuals. We call the estimate made from a model the predicted value and write it as y hat to distinguish it from the true value y. The difference between the observed value and its associated predicted value is called the residual. This value tells us how far off the model's prediction is at that point. To find residuals, you have to subtract the predicted value from the observed value. Best fit. The line of best fit is the line for which the sum of the squared residuals is smallest. The line must go through point x hat, y, and y hat. The value of m is the slope. Larger magnitudes of m indicate steeper slopes, negative slopes show a negative association, and a slope of 0 gives a horizontal line. Each predicted y tends to be closer to its mean in standard deviations than its corresponding x was. The property of the linear model is called regression to the mean, and the line is called the regression line. R squared. The squared correlation, R squared, gives the fraction of the data's variation accounted for by the model, and 1 minus r squared is the fraction of the original variation left in the residuals. Finally, the slope of the best fit line for z-scores is the correlation r. The slope of regression line is b1 equals r times sy over sx. The equation notation for the regression line is BO equals y hat minus b1 times x. The unit of the slope is always units of y per unit of x.
As we know, a linear regression model follows the y hat equals b0 plus b1 x model, where b0 equals y-intercept and b1 is the slope. Sometimes, however, one must find the value of points not directly represented in the model. This can be done through extrapolation or interpolation. Interpolation operates on the assumption that the line of best fit, y hat equals b0 plus b1x, is a good measure of the data, within the confines of the data, by plugging an x value not given, but between two values. Extrapolation operates on the assumption that the same line of best fit is a good measure of the data outside of the confines of the given data. This is found by plugging an x value outside of the given data and assuming that the line of best fit will still be valid. In statistics, generally, interpolation is allowed while extrapolation is highly discouraged. This is due to the fact that for the most part, a line of best fit represents most points well within the given confining data, while a line of best fit may fail to represent all data outside given limits. A high leverage point is one on a scatter plot that greatly affects the line of best fit due to its inclusion in the dataset. This is usually the case when one point widely varies in x or y value from the rest of the set. This can also occur when one point's residual is very different than other points' residuals. This point usually shows up as an outlier when graphed on a scatter plot. A lurking variable isn't one that we necessarily assign a value to. Rather, it is something that is not expressed in the data, but still has a definite effect on what the graph appears to show. An example of this would be a graph comparing blood pressure to levels of alertness in a person. It is very possible that the amount of coffee consumed would be a lurking variable in this situation, as it would have an effect on both blood pressure and alertness, even though it had not been graphed in the scatter plot.